So, hello everyone. I'm very happy to introduce our today's speaker, Sheetal Wankhede. She is a PhD student at IIT Indore, working with Professor Swadesh Kumar Sahu. Her primary research area is complex analysis. More specifically, her research interests lie in geometric function theory, quasi-conformal mapping, complex integral operators, and univalent functions. So today she is going to talk on fundamental study of univalent function theory in the plane. Over to you, Sheetal.
Okay, thank you, Akansha, for giving me this opportunity. So let's start. So today I'm going to discuss just a fundamental study of univalent function theory in the plane. So we are just going to discuss the basics only here. So from calculus, as all of we know, the area under this curves is given by this integral a to b f of x dx. And this is nothing but the limit of this sum f of xi del x from Riemann integral we all know. So, so we know that when this f of x, when f of x equal to 1, this integral is nothing but it gives the length of this integral AB. So next we move from R to R square. So now we need to find the volume under this surface, which is given by this integral, which is nothing but is given by this summation. Okay. So same here. So when this f of xy is equal to 1, this integral gives the area of this region R. So next, our aim is to move from calculus to complex analysis. So we know this, we have in domain Z plane, and this f function maps this domain D to D dash. Now we need to find the area of this region D dash. So this is nothing but is given by this double integral over this region D dash du dv, which is given by this integral, and this quantity is called the Jacobian of this function, which is also denoted by this quantity. So next, we see most importantly, and here this dr I denote with the disk of radius r, and r lies between 0 to 1. So in this setting, r for r equal to 1, this d represent the open unit disk. Now we see some image of the unit disk under some complex function. So under this function 1 minus z, this unit image of this disk is again disk, because it is just a translation of identity function. And under this function 1 minus z square, the image of this unit disk is cardioid shape. And under this function 1 minus z to the power s, where s is some 2 times 1 minus beta e to the power iota alpha cos alpha. For some values of alpha, we'll get this image, and for different values, we'll get this image. So now we all are familiar with the analytic functions, but just I need to revise it. We know this function is said to be analytic in this disk if it is differentiable everywhere in this disk. So we say for a point, a function is differentiable in some neighborhood of this point z0, then we say this function is analytic at z0. So, and the most importantly, what is univalent function? So univalent function is a single valued function is said to be univalent if it is analytic and 1 in this unit disk. Okay, so here I'm going to use some notations. So first notation is this mathematical A. This denote the class of all analytic functions f in D, having the Taylor series expansion f of z equal to z plus summation n equal to 2 to infinity a n z n. Akansha, hello. Sorry to
Yes,
interrupt.
yes, Sheetal.
Is it the same slide showing to you what I speak?
Yeah.
Okay, fine, fine. Huh. So next I'm denoting this S. It denotes the subclass of this classes. So the function belongs to A, and if the function is 1, so that function belongs to this class S. And this class we call the class of all univalent functions in D. Next, I have to denote this delta of RF. This denote the area under this range of this function F. So this area is given by this integral. And this is most importantly, we are going to discuss here. So we are going to first see the leading examples of this class S. So this Kobe function plays a very important role in this class S, and it is given by z by 1 minus z square. In series expansion, we
Sheetal,
can see like this. Yes,
Sheetal,
yes.
can you please show me the previous slide. I just missed that actually.
Okay, okay.
Just,
This one?
just
Yeah.
no, just previous of this.
Previous of this slide?
The last point is the area of f of
This, this,
z is
this
f of
del of RF,
right. Just RD
uh,
yeah. Fine.
this is not,
No, no.
this just represent the area of this
Just
function F
represent.
for radius R.
Fine.
Okay,
Yeah,
okay,
you can carry.
okay, okay, fine. So this Kobe function plays a very important role in this class S, and this is a series expansion, well known we can see, and we can split this function in this two form. So we can easily see the image of unit disk under this function K of Z. Okay, so this function maps unit disk onto the entire complex plane minus only this negative real axis from minus infinity to minus 1 by 4. Okay, so we see how it will work. So first we have the unit disk. So this function 1 plus z by 1 minus z. We all study Mobius transformation. So from that we can easily find the image of this disk under this Kobe function. So first this function 1 plus z by 1 minus z carries this unit disk to the right half plane. And then just we make the take the square of this function and 1 by 4. So this zeta function, what it will do, it just double the argument of this function and will get the whole complex plane minus only this negative real axis. And just only we shift by minus 1 by 4 and we'll get our required range. Okay, so another one more important function of this class S is this z by 1 minus z, which is simply summation n equal to 1 to infinity zn. So this function also maps unit disk onto the half plane. So which half plane we'll see? Simple, we use simple complex analysis. We denote this function by W and just replace in Z, and we know mod Z is less than 1, and using the basic complex analysis we'll get real part of W is greater than minus half. So this function maps unit disk onto this half plane, real part of W greater than minus half. Okay, so this is the image of this function L of Z under D. So next, third more important function we get this 1 by 2 times of log of 1 plus z by 1 minus z. So this function maps this unit disk onto these horizontal strips between minus pi by 4 to pi by 4. So simple here also we'll take this function w 1 plus z by 1 minus z, which maps this unit disk onto this right half plane. And then this composition of these two will give this. And this function 1 by 2 log w maps this right half plane into this image. Okay, so here also we can see the proof of this. Simple, we choose this function as 1 by 2 log of 1 plus z by 1 minus z and take log on this side, and we can simply see this calculation. Okay, so next important, my aim is to show this classical Parseval's uh, Guzmar formula. This is also called area theorem. Okay, so we already in introduction see this del of RF denotes the area of this range of this function f of dr. So here we see area we can find in terms of the coefficient, Taylor coefficient of this function f of z. If we have this function, analytic function f of z, which has a Taylor series expansion n equal to 0 to infinity n zn, so we can get the area of this function in the coefficient in Taylor coefficient form. So first we have to prove these equalities hold, that this integral value 0 to 2 pi modulus of f of r iota theta square d theta is 2 pi times of this summation of mod n square r to n. And applying this formula to f dash, we can deduce this area of this function n. So we see one by one the proof of this formula. So simple complex analysis we use to prove this. So we have this analytic function in this disk mod z less than r. So we can use the Cauchy integral formula. From this we have an is equal to 1 upon 2 pi iota and integral of this value. So next, first we compute this term, integral 0 to 2 pi and these conditions. So just we split the mod square into two parts and f of r theta, we keep it as it is, and we write this f of r iota theta mod in their series form. Then simply just for this an, take all this term out. Okay, up to now it's okay, fine. Huh. So by uniform convergence of Taylor series, we can take this summation out and integral inside. And here, just do the arrangement of term. And this we know, this is again an by this Cauchy integral formula. And we'll get this for first formula, what we explain here, this formula. And if this formula you apply for this f dash of Zn and put here in the, let me show you. If you remember here. Okay, so we have this integral value 0 to 2 pi and this integral in terms of series, and you can put, and we can get this area theorem. So we can get this area. So importance is that only if we know some function and their Taylor series expansion, so using that we can find the area of this region. Okay, so next we see some example of for this. So we choose this Kobe function. Okay, so for Kobe function, we have this Taylor series expansion. So here our an is n, and we just put this an equal to this in this area theorem, and we got this when solving this series, we'll get this. So here as r tending to infinity, r tending to 1, we see this area goes to infinity. And already we see this Kobe function maps unit disk onto the whole complex plane minus this slit only. So we verify from here. So one observation we can make, if we take z by this Kobe function, which is 1 minus z whole square, and this function maps disk onto the bounded domain. As we already see there, this function maps unit disk onto this cardioid. So what can we say about in general when we took f belongs to S class? So what can we say about this function? So for that, okay, so we choose function f from class S, and this z by f of z, all obviously a non-vanishing analytic function in D, and so we can have the Taylor expansion for this function also. So using that, this Yamashita proved this area theorem for this z by f function. Okay, so they proved that maximum of all the function belongs to S, then area of this function z by f is given by 2 pi r square times of 2 plus r square for r lies between 0 to 1. And maximum can only be attained by the rotation of the Kobe function. Okay, so I'm not including proof of this. So next two important things are, first we have distortion theorem. So distortion theorem gives the bounds for the derivative of the function when function belongs to class S. And these bounds can use to prove so many important theorem in the univalent function theory. So we have modulus of this mod of f dash of z with the upper bound 1 plus r by 1 minus r the whole square, and the lower bound is 1 minus r, 1 plus uh, r the cube for all z belongs to D. And here also equality holds for the suitable rotation of Kobe function. That's why we call this Kobe function. One second. This function, if you remember, this is an extremal function in class S. Okay, so next one is growth theorem. So growth theorem gives us the bound for this function f, which have this lower bound this and upper bound this. And here also same the equality holds for the rotation of Kobe function. So next we have to introduce some subclasses of this class S. So for the subclasses also, the area theorem is introduced, and this capital AR denotes the maximum of all the functions belongs to this subclass del of f, del of r z by r. So there are two important subclass here we are going to mention, this class of convex function and class of starlike function. So they both are the subclass of this class S. Now we need to find the what is the value of AR for these two classes. Okay, so what is convex domain? So we know that the domain said to be convex if the line segment joining, okay, if the line segment joining any 2 points in D lies entirely D. So same concept. So now the class C. So the class C is the function f is said to belongs to class C if f of D is convex domain. That means we have one function f which maps this unit disk onto some convex domain. Then we can say this f is convex. Okay, so we see this image. This is convex function and this is non-convex function. So because the line joining these 2 points are not lies in that domain. Okay, so here this function z by 1 minus z, which is already we discussed, this function plays an extremal role in this class. That means whenever we have some properties for this class, so in that case, equality holds for this function. So there are some characterization from which we can find which functions are convex or not. So this is the characterization for this function. When we have this function belongs to this class A, and real part of 1 plus z f double prime or f prime is positive. So we can then, in that case, we can say this f belongs to class C. Okay. So we'll
Sheetal,
see the
can
proof.
you please
Huh.
uh, re- repeat that? What is that script A? That
Okay.
this class? What is the definition?
Okay. Hmm.
The
So,
class A. What is this class A?
okay. First class is, 1 second.
Is
Class A
univalent
means
and
F
other
is,
property
F is analytic, not
and
univalent only.
univalent.
F is analytic and F of,
Analytic.
sorry, I use pen. That means F is analytic, simple, and f of 0 is equal to 0, f dash of
Oh,
0 equal to 1. Only this condition.
uh,
Huh.
no,
S is a
not univalent.
subclass of
Not
A. Huh. Then that net will be. So it will come
oh.
inside that. Okay. Huh.
So in univalence
Yes.
is not assumed in the class A, right?
No, no, no,
Uh,
no, no.
okay, okay,
Here we don't need to assume univalency. Already
okay,
when
okay,
we prove it, it comes univalent.
okay. So my
Huh.
question is, if F is a convex mapping,
Hmm.
then from Dix to let some convex domain, then
Hmm.
univalence is not necessary, right?
No, no, univalency is necessary. I am saying that to prove this characterization, I'm saying
But
that when f belongs to class A and
uh,
real part of this function is
no,
positive,
that
then
yeah.
automatically f belongs to C and C is already a subset of S.
Okay, okay,
Huh. If you choose f from S, that's already, but you can choose f from directly, it will automatically coincide to this S.
oh, okay,
In proof, we'll see because they are just mapping. Let me. Huh. Is some place.
okay.
Huh. Actually, unit this when we say f maps to some convex domain, they will just map this circle to circle. They will not coincide. So automatically they come univalent and the domain shape is convex.
Uh, okay.
Huh. So that's why when we prove this characterization, we are choosing from function only analytic and this. Okay. In proof, I'll
Fine.
tell you. Huh.
Okay.
Okay, so simple proof of this characterization. So I am just give some sketch of this proof. Not so we know this function f of z belongs to class A if and only if f of dr is a convex domain. Okay, so geometrically, when we see the figure of this convex domain, what we say, this function f maps each circle onto this curve CR, which bounds the convex domain. Okay, hello.
Okay. Ah, it's fine.
Huh. So here actually each circle, this function maps to the curve which is bounding this domain and they will not coincide,
Mm.
intersect each other.
Right, right.
Huh. So the convexity implies that, and we know the complex convexity implies that the tangent to the slope of tangent to this curve is non-decreasing as theta increases in the clockwise direction. So that thing, this thing we write in analytic manner. So that means what? This is slope. This denotes the slope of tangent. Okay, and to show this slope is in increasing mode, that is del by del theta of this quantity should be greater than 0. Okay, so simple, first we take the derivative of this function, which is I r e to the power iota theta and f dash of r e to the power iota theta. So when we apply the argument of iota we know pi by 2, argument of this is theta and plus, okay, r will not be, our argument is 0 and this is argument of f dash of r e to the power iota theta. Okay, and we know the argument is imaginary part of log. So just we put and we take imaginary part out and take derivative of this log function. And we know that imaginary part of iota z is equal to real part of iota z. So that we apply here on and we get this. This. So it is clear.
Yes, yes.
Huh. So simple. Okay, simple analysis we put here and just we get this characterization from geometric condition to in terms of analytic function. Okay, so for this class of convex function, we get the area of this function z by f is pi r square always. And the maximum is attained only by the rotation of this function z by 1 minus z. So simply here we can easily say for the maximum value that z by f will be here 1 minus z. And this is nothing but the translation of this circle. So it will give the area. Okay. So next we move for the starlike domain. So a domain is said to be starlike with respect to one point W naught if the line segment joining that point to other points in W lies entirely in D. Suppose I'll make this type of domain. Okay. And this is my W here. Okay, so from W naught, I can join every point. But suppose I took this point W1. From W1, I can't join this point. So that's why this domain is star-like with respect to W naught, but not star-like with respect to W1. Here we see. So that's why star-likeness property is about the point. And similarly, the function is said to be star-like if f of d is a star-like domain with respect to here. So one more thing. Sorry. When I set this class S star denote the function star-like with respect to origin. Okay. There W naught can be any point. When W naught is 0, we can that function belongs to this class S star, the star-like domain with respect to origin. So here we see the image of this star-like domain. So this domain is star-like with respect to W naught. So that means we can join W naught to any point other with W and we see this argument of the function. So here that means angle made by angle should be this argument of f of z made by this W naught and any other point of this curve should be in increasing mode. Here we see. So if I see this theta argument, so argument is going to increase. But I suppose I made this type of domain. Uh, Suppose this is my W naught. And now see this W naught is not star-like. With this point, I can't join a line which is completely in that domain. So here we see that theta is increasing. Okay, but for this point again that theta goes here from here to here, that argument is going to decrease. That's why geometrically what condition implies the star-like domain function to be star-like is del by del theta of argument of f of r e to the power iota theta should be positive. That means this argument of the function should be in increasing mode. So here one remark we can make that convex domain is what it should be a star-like with respect to all of its point. If the domain is a star-like with respect to all the point, we can say domain is convex domain. So similarly to convex function, we have this characterization for the star-like domain, star-like function also. So here, when the real part of z f prime or f prime is f prime or f is positive, we can say this function f belongs to this class S star. Okay, and the extremal function in this class is again Kobe function. Because if we remember the Kobe function, so this is a Kobe function. So this is a star-like with respect to origin. We can join any point with origin, but we can't join this 2 point. So that's why this Kobe function is star-like but not convex. Okay, so we see the sketch of proof of this for this characterization. So here already I mentioned this function f is star-like if and only if this f of dr is a star-like function. That means this function f maps each circle onto the curve CR which bounds a star-like domain. Okay, so geometrically already we see that means it follows that this argument of this function increases as z moves in the clockwise direction around this circle mod z equal to r. So this is a condition. Again, we reduce this condition in the real part form. Similar way, just we have this, okay, del by del theta of argument of this positive, and then this is nothing but the imaginary part of this log function, and we'll take derivative and just replace with imaginary image of iz to real part of z, and then we'll get this. And we know this can't be equal to 0 by the maximum principle of harmonic function. So that's why this real part of this is always positive. So next important thing, we have this Alexander theorem, because this Alexander theorem gives the relationship or connection between this class of convex function and class of star-like function. That means if you have one convex function, you can generate one star-like function and vice versa. Okay, so this Alexander's theorem also mentioned in terms of integral also. So in other words, Alexander says if phi is a star-like function, then this j phi is belongs to k, where this j phi is integral operator 0 to z phi of zeta over zeta d zeta. So in this connection, we can make it similarly to this. If we take the derivative, we have this j dash phi z is equal to phi z, similar to this. So whenever you are here you see, whenever your phi, that means your j phi is convex, z times j phi dash, which is your phi is star-like. And this integral operator also is very important in this integral operator theory. Okay, so next class we have this class S star beta, which is a subclass of this class S star. So for beta belongs to 0 to 1, this class, when the real part of this is greater than beta, we this class is denoted by S star beta. So simple, there we see when this part is greater than some, it denotes some half plane, then we say this F belongs to S star beta class. Okay, so an extremal function in this class is this z by 1 minus z to the power 2 times 1 minus beta. Beta belongs to the same 0 to 1. Okay, so one observation, if we see for beta equal to 0, this class is coincide with the star-like class. Okay, and here when beta is half, this class of convex function is a subclass of this S star of half. So some open problem in this direction I want to mention. So one open problem was for the related to this Yamashita's conjecture was made by Punuswamy and Fritz, and that problem was settled by Punuswamy and Sahu and Navnit Lal Sharma in this paper. Okay, so this is an unsolved issue. When this function belongs to sec of beta, then what is okay?
Sheetal, what was the open problem? Can you go back to the slide?
This I'll mention this next slide. What I'm
Okay,
this one
okay,
this one.
okay.
That. So already we see for the class when f belongs to S. So this is there that area of this function z by f when f belongs to this C beta class. C beta class is generalization of this convex class. So what is the area of this function? So that was settled in this paper. Okay. And one more conjecture was given by Sahu and Arora, that when this function f belongs to class S, and then when this mu is not equal to half, one positive number, then the area of this function z by f to the power mu, they generalize this function with some parameter is less than equal to 4 pi r square mu square, and in the form of this hypergeometric series. And again, this equality is hold for Kobe function. So when the case mu equal to half, they already proved that paper. I could not. Oh, sorry, I forgot to mention this paper here. Okay. And third, more important is this Zelkman conjecture. Okay. So Zelkman conjecture is that when we have this function f belongs to this class S, then the modulus of an square minus a2n minus 1 is less than n minus 1 square. And again, the equalities hold for here Kobe function. And the importance of this Zelkman conjecture is this Zelkman conjecture used to prove this. And this is actually a very important conjecture called Bieberbach conjecture. Bieberbach conjecture that I'll mention later. This is a basic of this univalent function theory. From there, the development of this univalent function theory start. Okay, so I need to mention here this Bieberbach. Bieberbach gives this conjecture. So first he proved that when the function f belongs to S, then he gave the modulus of this second Taylor coefficient. Then he said that mod of this A2 is less than equal to 2. And then he state this conjecture for all n, that mod of an is less than equal to n, and equalities hold for this Kobe function that we can see easily. But this conjecture he can't able to prove. He only prove for A2. Then next, that conjecture he made in 1905. Then 1923, this Charles Lawner, American mathematician, he proved that when f belongs to S, then only he can able to prove for this third Taylor coefficient. And during when they are trying to prove this bounds, they will generate so many good theory which is useful in other mathematics also, and in this univalent function theory also. Then later all this Garabedian and Schiffer, they prove for this four Taylor coefficient in 1955. So and then in 1966 this Pardison and Ozawa prove for the six Taylor coefficient. And then later on D. Brange. D. Brange, after 68 years, he proved for this, for all coefficient, for all Taylor coefficient, that this inequalities hold. And when the De Brange proving this coefficient, he investigates so many good theory in this geometric function theory. So this is the key. He play a key role in inventing this geometric function theory. So next we are moving for this harmonic mapping. So and in the proof, this proof is very lengthy, so that's why I can't able to attend here. So when De Brange is trying to prove this, so he used so many other theory like operator theory, so many fixed point theory, so many theory he tried to use this inequality. So next, the important area in which I am working is harmonic mapping. So I'm just giving the basic of what is harmonic mapping here. So already, so we see this function, real valued function, is called harmonic if it has a second continuous second order partial derivative and it satisfies the Laplace equation. Okay, so now what is a complex valued harmonic mapping? So we have this complex valued function f of z at u of z plus iota v of z, and we say this is harmonic if its real and imaginary parts are harmonic. So we know this u and v are real valued function, and when they satisfy this Laplace equation, we can say this f is a complex valued harmonic mapping. Okay, so we have one canonical representation which represent the harmonic mapping in terms of analytic function. So in simply connected domain, we can say the complex valued harmonic mapping F has this representation H plus G bar, where this H and G are analytic function. So when we are able to represent the harmonic mapping in terms of the analytic function, we can we can explore all the theory which is already available for the analytic function for the harmonic mapping. So whatever already all the classes, all the property we discussed, that is all then extend and generalize for the harmonic mapping. Because when G is 0, harmonic mapping is already an analytic mapping when F equal to H. Okay, so for this harmonic mapping, one more important term is needed, that is called deletion. So this function W of Z, which is f of z bar over bar f of z, is known as complex deletion of f. And then this f equal to h plus g bar is harmonic if and only this W of z is analytic function. So when we have f equal to h plus g bar, we can reduce this to quantity, and which is g dash by h dash. Okay, so one more important thing, already we discussed convex domain. Now we see domain convex in particular direction, in one direction. So we can say a domain is said to be convex in this direction theta, where theta lies between 0 to pi, if every line parallel to the line through 0 to e theta has connected an empty intersection in D. I'll make some domain. Suppose this domain. Mhm. I'll make it like that. Okay, now we see this domain is not convex, but this domain is convex in some direction. So first I have to see in which direction. Suppose I put theta equal to pi by 2. Here is my theta. Now I see every line parallel to the line through 0 to e to the power iota theta. These are the lines, okay, parallel to this line 0 to e to the power iota theta. Now if we see this line has connected intersection with this domain, or otherwise empty intersection. Okay, so we can say this domain is convex in the direction of pi by 2, or we can say in vertical direction. Got it? Okay. So in particular case, here we need actually to construct a harmonic mapping CHD domain. Okay, so a domain is said to be convex in horizontal direction if its intersection with each horizontal line is connected and empty. So if we compare with this, that means when our theta is equal to 0, okay, then we can say this domain is CHD. Like I am preparing this. So now if we see, we take the domain's intersection with all the line parallel to horizontal line, they are have connected or empty intersection. So this domain is CHD domain. But this domain is not CHD. Okay, why? Because when I took these lines parallel to this x-axis, they have not connected intersection. They have disconnected intersection. So this is non-CHD. Okay. So for that, very important method was given by Clooney and Shellswall. It's called shear construction. Okay. So they introduced this method to construct the harmonic mapping from the analytic function. So shearing means actually here stretching and translating. That means we have one analytic function and we stretch that function through this dilatation W, and the deforming geometry which is coming, this gives you this harmonic mapping H plus G bar. So how will we do? So there is one algorithm, okay, given by this Lunian and Small. What they said, to construct this harmonic mapping H plus G bar, first we have to choose CHD conformal mapping H minus D phi. Okay, phi we choose as H minus D. Suppose I have CHD map this domain. So this is my phi, which is equal to H minus D. This is one analytic image of some analytic function. Okay. So now what this is, choose a dilatation W. So I already mentioned W what will do, it shears or stretch, translate anything it can do. So using this W, it will stretch, shear this mapping. W will shear phi, and we'll get some other geometry, and that will give you this harmonic mapping. So analytically, how we do? So we choose this phi. Okay, we choose this analytic function phi, which is denoted by H minus G, and we choose this dilatation W, which is G dash by H dash. Now we solve this system of equation. We can take derivative of this, and we can find H and G, solving this system of equation, and we can construct this harmonic mapping using this H and G as H plus G bar. So thank you so much. If there are any questions.
Yeah, thank you, Sheetal. Yeah, does anybody have any question? So, if not, let's thank the speaker again. Thank you.
Thank you so much.
Okay. So, I'll end the meeting now.
Thank you. Thank you, Akansha.